like EnergyToolBase because when I'm doing commercial solar sales, there's nothing better than getting the CFO to smile and presenting a CFO with a clear and accurate depiction of the true project economics is is you know the first part of the conversation. And the second part is it a good economic deal or not? And if it is, then you got your project. So, um, I would take engineering economics classes in college and be trained to produce cash flow diagrams like this. It's evident that EnergyToolBase knows what they're doing in terms of economic modeling. So it's a very accurate economic modeler. Uh, Particularly useful for commercial. You know, the same level of detail that Aurora brings to its 3D modeling, EnergyToolBase brings to economic modeling and visualization of site energy use. So the best way to use EnergyToolBase is to have interval data, 15-minute usage data of a facility, and most commercial businesses should be able to get this data from their utility. Some residential sites have it as well. But what we're seeing here is a day where, back in here, dark blue, the building's energy load is normally, and then we have a solar array that turns on in the middle of the day. And so the new building load, it has this, instead of having a big, tall midday peak, it has a little morning peak and then a little afternoon peak. But the solar array has reduced the building's peak demand throughout the day, and so that's good. Demand electricity is expensive, but most solar installers who have looked at commercial solar know that the true demand savings for this day don't matter if the very next day you have a partly cloudy day, and so the building's demand, if the solar array turns off because that one cloud in the sky has inconveniently located itself on top of your array, if that's the case, there's no demand savings for the entire month, because demand savings are calculated not on a day-to-day basis, but what is the maximum 15-minute period of peak demand, and that can comprise, in some cases, 70% of a commercial electric bill, and sometimes more. It can get real extreme. And so what EnergyToolBase does is it takes your interval data from your building and your PV watts, hourly data, and then you can also add a battery. And so now what it's modeling is, okay, this is a partly cloudy day, but on that time when the building load would normally be high, but the solar array is turned off, we're running a battery to keep that building consumption level. And so all of a sudden, commercial solar becomes possible for economic project work, whereas in the past, we have not had batteries. And so commercial solar was this random, chaotic mess of very little economic return. Now we have solar sitting on top of a commercial building, providing demand electricity, and a battery that only runs for a very small amount of storage. That's only storing maybe 3 or 4% of the total facility's energy use for the day, or maybe even less than that. But we're just we're not trying to do the entire electric bill of the building. We're just trying to shave off the peak in a cost effective manner. What's even more interesting is if the client didn't have budget for this large of a system, just focusing in on the very peak can be even more cost effective. And so small projects in this space, a solar array with a battery that is a system for a large luxury residential, that same system, you go and put it on top of a commercial facility, and the payback might be, in 5 or 6 years instead of 12 or 13 years. Or the payback might be in 10 years if the payback would be 20. It can, the most cost effective payback in solar right now is in the commercial sector doing these kind of solar peaker plants. So EnergyToolBase even has my little electric cooperative in coastal Mississippi in their rate database. So what they have found is, despite all the utility rate tools that are out there, the most accurate way to model rates is to open up every single one in the entire United States and program it into a database. It's not a perfect process, but a company whose job it is to keep track of that stuff is going to do it a little bit better than what you can do on your own. Um, and for the most part, it works great. I work in some pretty rural areas in Mississippi, and if something works, we're happy with it. It doesn't have to work great. Uh, anyway, I just moved apartments, and I was taking a look at different rate structures. And even though my electric cooperative does not have a very good solar policy, they have a pretty interesting time of day rate structure. And so in the summertime, between 3 p.m. and 6 p.m., Monday through Friday, I have this peak rate and off peak all other times. And in the winter, instead of being a 3 hour period, it's only a 2 hour period. Again, weekdays only, off peak other times. The meter fee for time of day metering or regular with this co op is the same either way. Without time of day metering, I get a flat rate of 9 cents a kilowatt hour. With time of day, during the peak period, the electric rate quadruples. And then during the off peak period, the electric rate gets cut, in half. You still have this rather large meter fee. But let's just take a look at this. If it's 3 hours a day, 5 days per week, that's 9% of the year. Well, they call it peak for a reason, and so let's just fudge our numbers a little bit on the conservative side. Let's call it 10% of the year. So for 10% of the year, during that time frame, the electric bill will increase by 400%. And for 90% of the year, the electric bill will decrease by 50%. So let's assume you're either by having a solar array that's on during peak times, or having a battery that runs during peak times, or by, what I do is I use my home automation system to change my thermostat settings and turn my heavy appliances like my electric water heater and refrigerator off and coast through the peak time. So I solve this issue without solar or batteries. And that gives me about an even load distribution, without solar or batteries during those peak times. So I do some load shifting to reduce my energy during peak times in an automated fashion. And so 10% of my bill is going to increase by 400%, and 90% of my bill is going to decrease by 50%. And what that gives me is a 5% monthly reduction on my electric bill by switching over to time of day metering for doing relatively nothing. If I went further and really, throttle that thermostat. If I said, I want to turn my refrigerator off for 3 hours, and so, I'm going to get two refrigerators and fill both of them halfway up with thermal mass and just completely kill them total uh, for those 3 hours. If I went extreme about it, I could, if my peak energy use is half of an even distribution. If I go very Spartan with my peak energy use, my electric savings could be 30% or more, before I get into storing it into a battery. And so sometimes these time of day rate structures can be particularly advantageous. Batteries are interesting. Batteries mean that we don't need to generate all of our electricity. We don't need to store all of our electricity. Maybe we can do exactly what is just right to optimize it to our rate structure for the greatest, return on our investment. And so, Energy Toolbase will model the state of charge. I think it's very useful to get into the Energy Toolbase data and try and tell yourself, okay, well, on this day my battery is being used, but I'm not fully draining it down to zero. On the next day I am draining it down further. So what's different between the first day and the second? Oh, we have a larger midday peak, and that takes it all the way down. And so if I wanted to make sure, if I had a larger battery, well, then I would not just be shaving this peak and this peak, but also that peak. And so now I'm running my battery more. If I called this base load and downsized my battery, then I'd only be looking at a system that maybe did that much. And so by being able to kind of see the data, you can hone in on, what the optimal system is for cost effectiveness. And they have some optimizing algorithms built in to kind of steer you towards the best system size. Here we're modeling a time of use rate structure for during the week, and then a separate rate structure for weekends. So we're modeling our off peak period and our peak period. What I did is I just went and modeled it without solar or without batteries to see what switching to time of day metering would do. And so, I had to go and plug in my energy data. Now, I did not have the interval data to plug into Energy Toolbase. I did not have green button data. All I had was my month to month electric bill. And so I was able to log into my electrical account and get my consumption history for each month, but that's it. And so what Energy Toolbase does in that is you plug it in, and then you have to go and tell it, okay, what part of that's going to be peak, what part of that's going to be off peak. Um, and so I modeled about 10% of my energy in that time frame being priority peak. Um, here we're able to select between the flat rate and the time of use rate. And so, I didn't actually get all the way through their reports. I just looked at, what's nice about um, Energy Toolbase is some of the numbers it puts in the corner and it calculates as you're changing things around, so you don't have to get all the way to the report to see how you did. But in short, what I found is that just by kind of doing nothing, I could save about $300 a year off my electric bill by switching on to the time of use metering structure. And if I kind of kicked up my digital controls, I could save as much as another $200 while still using some peak energy even without solar or batteries. And so I'm potentially saving uh, you know $300 to $500 a year in electric savings, by implementing smart home technology, and also taking advantage of this time of day rate structure. So that's kind of interesting. If you have the option of a couple different rate structures, you might find that the some of the best savings from the system could come from just switching them to another rate structure. And so, maybe they don't need to know that, and they won't really care if the savings come from the different rate structure or from the solar array on top. They'll be happy to see their lower electric bill. And so here we have some more looks. Here's helioscope integrated right into EnergyToolBase. I think helioscope is making good strategic alliances to kind of be that default 3D shade modeler. We're putting in the array size and the array cost and the tilt angle and the orientation. Otherwise it's just going to get its data from PV watts. So here's our PV watts info. After you build your solar array, you build your battery, and so I think the battery component is really where it's at. It does battery modeling very well in ways that other softwares just aren't even thinking about. Um, so we're putting in the size of our capacity, the maximum discharge power. That's going to vary wildly from lower end lithium ion to higher end lithium ion. Um, so you do have to know a little bit about batteries. We have battery classes where we talk about these things in greater detail. Um, so then it kind of tells us that the larger the system gets, the lower our effective savings go. And so, maybe starting out with a smaller battery is actually going to end up to be more cost effective than doing a large battery, which makes sense because a smaller battery only handles peak energy. A larger battery will get into base load. The closer you get to base load, the less cost effective that battery will be. Um, I was interested in seeing, okay, well, how do I know this model is working? And so here we have the solar array and the battery, kind of only being charged by the solar array. So the battery is only being charged when the solar array is on. So that's a mode of operation for the battery. If you charge the battery with solar, then it qualifies it for the tax credit. We can see that the solar array is really too large. There's a lot of energy being exported to the grid, and so it if we're in a situation where the outflow onto the grid does not have a lot of value, there's really no need for the solar array to be this large. It could be a good even half the size would be too large. It could be a third the size and still be reducing peak load during the middle of the day and providing enough energy to charge the battery. And so in here, we're programming it to target energy arbitrage and rather than demand savings. These can be a little finicky to play around with. Nothing too complicated. And generally, to make sure I know I've set my settings correct, I'll go in and look at the visualizations just to make sure the system is charging and discharging that battery when I want it to. And so here we have a couple of different configurations, but you might be modeling it for solar or solar with without the battery, or the battery without solar. And so what we see is here for a $10,000 10 kilowatt hour battery, uh, the battery is going through 129 cycles a year, and each kilowatt hour is saving it $38 through per kilowatt hour. And here we have a larger battery that's going through fewer cycles, and because we spent more money on it, it's not saving us as much money per kilowatt hour. And so I look at the effective generation rate, the effective cost savings of using the battery per kilowatt hour, and kind of size my system smaller and smaller until the numbers start to be good. And so what that might mean is here's a battery that we wanted to run for 3 hours in the middle of summer, and not buying it to be much more than that. And so we're looking at that one day in summer, on the peak day, on the day of maximum usage, and seeing that our battery discharges down to like a 23% state of charge over that period. And we say, okay, we don't need a larger battery than that, than the highest day's use plus 20% margin. That's that might even be 20% too large for that matter. With time of use metering, not like a commercial kilowatt demand charge, but time of use metering, if you have some kilowatt hours where you're paying that peak rate, it's bad, but it's not as bad as uh, running out of battery capacity for demand savings. And so now we have a report that tells us how much is solar and how much is batteries, and what our system payback is going to be. Um, how much of our power is generated on site. Some nice economic graphs, and we get into our cash flow. Um, in the EnergyToolBase reports, there's a chart that gets into the utilization rate of the battery. And what I have found is that the less cost effective the battery is, the more it has a shallow utilization and not a full utilization. And the what the utilization rate is how much of the battery is used when it's being used. And so on this larger battery, the battery on the days of maximum discharge, maybe one day out of the year, it's being used to 80%. Whereas here, with a 5 kilowatt hour battery with something a quarter of its size, it's being used, almost every day to its fullest extent. Hopefully it's being used 5 out of every 7 days, right? And so it's the right, what is the right size battery, because lithium ion is very expensive. So you want just enough to get through your 3 hours of usage, because that's what the rate structure is, but not more than that. Some financial metrics, some words of advice. Let's just take a quick peek. Well, I don't know. I don't think we really have time in this program. Whatever. Let me log into EnergyToolBase, since I did get it set up for this class. And so here we are in EnergyToolBase. Some of this stuff should look familiar. So here we have a proposal. And so, if the economics don't look very good, that's because solar economics are not very good in Mississippi. It's probably the worst in the country. So, if you're taking this class in other markets, you probably have better economics than what are being shown. At the same time, that means in Mississippi, we have to be, very, very, aware of, not making the system so expensive that the client doesn't get any return on their investment. And so what I have here is honed in on a system that could have a 14-year payback. And ironically, it's a $9,000 system, and it's a very small solar array and a very small battery on a time of use rate structure. And that is because in Mississippi you don't get anything for outflowing onto the grid. It's just not a very good deal. And so here we've modeled our energy use and our energy charges. But what I like is the demand load profile, where you can just click on, let's say 3 days, and kind of see how the demand works. And if you wanted to turn off all the noise and just see the building load demand, what we see is during that time of day period, the building being turned off, and then right when we're done with the time of day period, the battery charges back up again. What I find particularly useful is, so it's showing us the kind of the, if we go and we look at our battery state of charge, we go and look over the entire month. It calls us out. What is our maximum time of use period before, and then you can say, okay, well, during that maximum period, when is that? That's right around January 19th or so. So we're gonna go take a look at that time frame. We go and we look at our, okay, so now we have a solar array coming on at the same time. So we can get into the solar array size, and here we have the system cost and the system size. Um, and we look at our, kind of our calculations that are built into it right now. We see our payback period down here in the corner at 13.7 years. If I said, okay, well, I know that if we actually did like a 15 kilowatt solar array, I could get that installed cost down to $2.50 a watt instead of $3 a watt, and click save. I don't have to get through the whole model. Now it says my payback period is 6 years. Well, that doesn't make sense. You know why that is because um, I put $3. Well, I thought I was putting $3 a watt. I put $3. Well, the system is not going to cost $2.50 for a 15 kilowatt array. That's going to be a $37,000, $500 system. And so now we go and see that the payback's 24 and a half years instead of 13 and a half. So, even though we got them a lower price on a larger install, because most of that is outflow, it's not worth anything, and so we have to only do little tiny solar arrays in Mississippi in order for them to be cost effective. Um, Unless we take the whole house completely off grid. That's another class for another time. Okay, so then we get to the energy storage component, $9,000, and so here's this blended savings number per kilowatt hour. And so if we wanted to say, okay, well, if we can do a 5 kilowatt hour battery for $9,000, so this would be a kind of a higher end lithium ion battery. Let's say we did a lower end like the Tesla Powerwall, but it's more capacity, and so there's let's say there's slightly more cost. So we're doubling the capacity, but we're only increasing the cost of the Tesla Powerwall to, or whatever it is, by a little bit. So $14,000 for 10 kilowatt hours, except it would be discharged over a 2-hour period instead of a 1-hour period. So now we see that blended savings figure has gone down, and we'd see our battery utilization rate go up. And so you don't have to get all the way to the very end where you're running a report to do it, but here we are at the very end where we're running our report and we're seeing our payback is not very good. So let's go back to our original 5 kilowatt hour for $9,000 battery. That would be like a lithium nickel metal cadmium battery, a lithium NMC. And now our blended savings, our generation rate is a little bit higher. So we're going to our transactions and saying 23.7 years, and it's like, well, that's not good enough. So maybe we delete the solar array. Our payback is about the same, with or without the solar array. It doesn't really matter one way or the other. And the payback on this particular battery is 22 years. So what we're seeing is that these high-end lithium ion in my particular market, it's not such a great deal. And so as a strategy, we're focusing right now on digital control systems that fine tune homes for time of use metering, by going after device level electrical load controls rather than complementing it with solar or batteries.